You can go. You can go. No, no, no. There's nothing important. I don't mind if you want to. Okay, good afternoon, everybody. My name's Philip Cardiff. I'm an academic in University College Dublin in Ireland. And I'm going to talk about solids for foam here. So this is mostly going to be an introduction to solids for foam. If you've seen it before, then I'm not offended if you want to leave. And then just at the end, I'll talk a little bit about some future directions as well. So solids for foam, what, why, how? So solids for foam is an OpenFOAM toolbox for solid dynamics and fluid-solid interaction. So actually, I was just at the multi-region foam talk downstairs. Maybe some of you were there. So actually the design, I would say it's probably a cousin of that toolbox. There's some shared code between the procedures and some shared philosophies, although they're probably more general. And maybe in the future, there will be more shared code. So the sort of things you can do, these are some of the tutorials. This is a dam break, but extended to have a flexible object. So it's the classic OpenFOAM dam break, but you just have an elastic structure. But also solid mechanics style research. So I've been involved in projects for metal forming, and some of this code ended in solids for foam as well. So it doesn't have to be FSI. So where can you find things about solids for foam? So if you can go to the website. So www.solids4foam.com has a lot of information. So some of the tutorials I'll go with are already actually described on the website. Anyway, so this, in case you're curious, it's actually just hosted on GitHub. It's a GitHub Pages. So you can pay $20 a year if you want to have the address. But it's on GitHub, so the website is fully open source as well. So you can fork the website and make a mirror if you want as well. And the website's actually just built in Markdown. So most of the tutorials are actually in solids for foam. And then when you push the solids for foam, it automatically will rebuild it and update the website on the other repository as well. So the documentation is with the repository. So just some background. So I guess if you think of computational solid dynamics, you think of finite element analysis. So people will often say CFD and FEA. So FEA is a numerical method and CFD is like a problem-solving method. So they're not actually comparable. So you would say FEA and FEM, for example. So FEA is one technique to solve PDEs, but finite volume methods and other methods have been used to solve solid mechanics. So since the early 80s, there's various different groups that have worked on finite volume solid mechanics. Some of the earliest publications were late 80s, early 90s. Notably, Demirjic. So Demirjic was the primary developer for StarCD. So he wrote a lot of papers in this area, and all the stuff that OpenFOAM does is very similar to this. Nabla, if you're curious, this was I guess, the owner of the Foam commercial software, the predecessor of OpenFOAM. But if you go to Wayback Machine, you can find their website and you can see what services they offered. There's no prices, but they listed solid mechanics as one of the many services that they offered. So it's slow to load this, but you can find, and they have some description of the methodologies that were used in the early development. So you can see here they have some residual stresses in a cooling jacket or something. So somebody gave them money to do something at the time, I guess. Or maybe not. Maybe that was a problem. So then in the early 2000s, there was a number of groups that would have worked on solid mechanics or FSI. And these led to some of the early developments in the foam framework and the related codes. And notably, you might have seen then later on this Extend Bazaar or this Foam FSI, or if you Google OpenFOAM FSI, there's lots of groups and they've shared code, and then there's some independent developments as well. My involvement was probably from the early 2010s. So in my PhD, I collected a lot of these solid mechanics code from the group in Dublin and then pushed it all to Foam Extend. And then solids for foam was kind of like a merging, a funneling of all of this into a design from 2016. So there's a lot of shared code with all of this. Why does it exist? So this, of course, maybe it's evident desire to solve FSI problems and solve mechanics problems natively in OpenFOAM. And initially, some of the original code, there was a solver called ICO FSI, nonlinear elastic updated Lagrangian solid foam or something like this. So if you wanted an FSI problem, you had to hard code the fluid solver, incompressible, compressible, whatever, and hard code the solid solver and then map it. So then if at runtime I wanted to switch the fluid solver or the solid solver, I had to write a new solver and hard code it all again. So that's problematic for various reasons. So this modular approach is much nicer. You can just runtime select the fluid, the solid, and maybe the coupling as well. So more recently, OpenFOAM.org also adopted this design. It's not that novel a design. It's commonly used across software, but also this multi-region foam use it. So there's benefits and disadvantages to this design. And then personally, I'm an academic. I'm just interested in numerical methods, and finite volume methods have some interesting characteristics relative to finite element and other methods for research. So even if nobody uses it, that's okay for me. The idea with the philosophy solids4foam, it's just a toolbox. It's essentially a solver and some libraries for OpenFOAM. So if you can use OpenFOAM, then it's intuitive to use solids4foam. We tried to support the main forks. I got in trouble for calling this fork, so variants, sorry. Fork implies that there's a predecessor in some way, and it implies that something's forked from something. So variants, I've been told, is a more appropriate term, but doesn't apply, suggest that one comes from another, which is some people think is important. So easy to install, emphasis on code design and style. I guess lots of people here, PhDs or researchers, are writing OpenFOAM code. This is the benefit of OpenFOAM. My experience is lots of them don't know that there's an OpenFOAM code style convention that is recommended to follow, so that when you send your code, people understand what to look for, rather than everything's on one line. And a single executable design. Just if you're curious, how can you support code between the versions? We use these compiler directives. So you'll see in the code, if OpenFOAM not extend, then if you want to take a reference, a non-const reference to the internal, non-const reference to a temp object, you would go like this, where foam extend uses the old version. So you have to support that. So this is the way you do it. This is not great for code readability, but if you can minimize it, it's okay. So what is solids4foam? The actual solver, which I'm using a capital F to distinguish from the project, it's a wrapper, and I'll give you a quick look at the code. So it's a wrapper that just calls a runtime selectable physics model, and that physics model can be one of three types. So it's a solid model, a fluid model, or an FSI model. And if you pick a solid model, then you pick a runtime, what type of solid model. If you pick a fluid model, what type of fluid model. So the fluid model could be pimple or interfoam or something like that, and the equivalent in the solids. And the coupling, assuming a partition coupling, is one particular method. So this is very similar to multi-region foam in its design. Okay, I will jump to the terminal. If I can get out of this. Okay, great. So I'm going to have a quick look at the code. I think this will be maybe too small, so I'll make it a bit bigger. Just a bit of a... Okay, is this okay? Okay, I'm going to use OpenFOAM 2312, but it should, I mostly use .com, so it should work with the 2506. I haven't seen if they made any major breaking changes, I don't think. So, okay, so if I maybe first, just the website. How can you get solids4foam? So if you just broadly follow these steps, this is not a bad place. So where do I start? Go to the installation guide, install from source. And then if you just run this command, this will clone version 2.2, and then that will download a folder called solids4foam. You go inside, run alt-wmake-j to use all your cores, and it'll build in a couple of minutes. So it's essentially just a library. It's some libraries on a main solver. And if you want, we have a basic test script just to check the cases will start and not crash. There isn't any mandatory dependencies apart from OpenFOAM. So if you try to run it and you haven't sourced a compatible version of OpenFOAM, it'll say you need to source a compatible version of OpenFOAM. Later on, maybe at the very end, I'll just talk briefly about some of the latest developments that are based on PETC. So in that case, you can go sudo apt-get install PETC, and you just have to set a PETC variable. or if you're on Mac, because I use Mac, I use brew, which is the equivalent of sudo app. So if after downloading solids4foam, I normally just put it the parent directory of the run directory, so the user directory. If I look at what's inside, okay, my font is huge here, so I can't see anything, but at least you can see something. So the structure is meant to follow the same structure of OpenFOAM. So you can't see very well there because of the color scheme, but this here says applications, and then there's an SRC folder and the tutorials folder. So it's meant to follow the design of OpenFOAM. So if I go inside applications, yeah, God, the color scheme is terrible, but yeah, so if I select it, it's colored on my screen, but not on this screen. Interesting. It's so subtle, so, okay, there's a folder called solvers and utilities. If I go inside solvers, there's only one solver called solids4foam. And then if I open up solids4foam, I'm getting a lot of wrapping here, but okay. So essentially just is a solver that creates the time, no create mesh, no create fields, because the physics model will decide what to do. So it's really just a wrapper solver that creates a pointer using runtime selection, OpenFOAM's classic runtime selection, to something called a physics model. Then we have a run loop, and then we ask the physics model, does it want to set the time step? Does it want to do some other random things? And we have an evolve function. Evolve function means solve your equations. So that could be an FSI physics model, in which case it might ask its fluid model and solid model to solve their equations iteratively, like and multiple times. And that's pretty much it. Then we have write fields, and then that's it. Physics.end. If they want, they could do something at the end. But it's essentially just a wrapper class. So if I go through an example, so what I'll do is I will go through a simple solid mechanics example, and then I will go through a simple FSI model, and then talk about some new steps. So slowly over all these trainings, I just build up many of these tutorials. So I'll just semi-randomly pick one. So I'm going to go through one. Even Pedistich added this to the website recently. So I think it's a nice one to show just how to set up a test case. Okay, so it's just a wrench. And the performance stress analysis on a wrench. So the boundary conditions are just going to fix the inside to represent it's in some way connecting to a bolt, and then apply a pressure to in some way mimic that it's being loaded and look at the stress distribution. Solving just small train linear elastic. This is kind of a classic, just simplest case for solid mechanics. And there's a variety of solution methodologies. So the OpenFOAM classic approach is this segregated Picard iteration. So we'll use that here, but I'll talk later about some of the other approaches. And then we'll expect to get something that looks like this. So I'll have all the steps. I've put these slides on my ResearchGate already. So if you just search for my name on ResearchGate and just see the most recently added item, you can download the PDF of these slides. So all these commands, I think I'll just use from the website. I think will be as easy. So we'll just go through it and hopefully it works. So after you've installed it, the next step is you can go through tutorials. So you can go through a bunch of other tutorials here, and these are all described. And these are just README files that are in solids4foam. So if you go to the case, it actually has a README with all of this, and this just gets rendered onto the website. So if I go to this fifth one called Open and Wrench, I will drop down to the first set of commands. So let's just really start from scratch. I'm going to over here. Make this a bit bigger. Okay. So I will make a directory called open end wrench and cd inside it, right? So I'm just in an empty directory, easy peasy. Next thing, I just want to get this wrench geometry, this actual zip. So you can download any one from somewhere. It's just we've just stored one on the website. So this command will just wget it. It just downloads it, unzips it, moves the files out, and deletes the folder and archive. So fine. So now we have a bunch of STLs. So these are the different parts of the wrench. For the commands below, even the way you added to make it easy, you've defined a variable called solids4foam directory, just so you know where that is. So you can add that to your bash if you want, but I'll just set a temporary variable. So I'll go export solids4foam directory, that's fine. So that's just defining where I've downloaded solids4foam, just to make life easier. Just hide these controls. All right. So we're going to use CFMesh, the free CFMesh that comes as a submodule in openfoam.com. So if you have not installed that before, you can just download it and build it like this. But I've done that, so I don't need to do that step. Okay, so the classic OpenFOAM way is find an existing tutorial, copy it, rename it, edit it. So we're just going to do that. So we're just going to copy the contents of one of the solids4foam tutorials called plate hole, and we're just going to copy the contents and put it in the current directory. So I've just copied constant system 0 hole 1. In other solids4foam tutorials, we use CFMesh, so you can look for mesh dicts out of you just using this find command. But I'm just going to take one. We have a tutorial called Wobbly Newton, this Isaac Newton's head bobbing around, but I'll just copy it from there. So we'll copy this. I think that put a split. Yeah, there's a space there that needs to be removed. So that's just copying in this system or this mesh dict, which CFMesh needs. So CFMesh is essentially runs like snappy hex mesh. And if I open up the mesh dict, the basic settings is you just give the name of the STL file or the surface file, and then a max and maybe boundary or some other settings. So in this case, we need to update that. And in the actual CAD geometry, the STLs we downloaded, all of the STL parts, all are just called object. So we should give them names because that's what the patches will be named. So this little for all bash script will just go through and just add a name based on the file. So I'll just run this to update the STL files. So that's just, if I look at wrench free, yes, it's a large file. So just at the top, it's just replacing this with the name of the file, just so at the patches, instead of saying object, which is where we downloaded it from. It's just changing the name because this will be used for the patch later on. So then if I just want to put all these STL together into one STL, which is what we need for the measure, you can just concatenate them. So if you go cat star STL wrench.stl, then we will have this wrench.stl file. I'll open that in the background. So then if I want to capture the sharp edges, I can mesh that directly, the STL, but if I want to capture the sharp edges, CFMesh use this FMS format. So it's essentially just wraps around the STL and encloses the definition of the feature edges based on a feature angle or something like that. Okay, that's just the STL in case we're wondering. Opens an X code, very good. So I'll generate this FMS file. So now I have an FMS file, which is has the feature edges described in it. So now I just need to update the mesh dict. So I'm going to go back to my mesh dict. I'm going to delete all the previous stuff. Paste it in. So our mesh file is going to be called wrench.fms. Max cell size is 16 in this tutorial. I will use bigger than that because the mesh is a bit fine. I want it to run. So I'll just set the max cell size of that and the boundary. I don't even think we need to define that. I think if we leave that out, it'll just assume that's the same, but you can use that as well. So we go 0, 3. And then if we just run Cartesian mesh, then it will create the mesh. Okay, pretty quick. Let's check mesh it. It has 23,000 cells. So let me open this in ParaView. Delete everything else I have here. ParaX or ParaX2 is just an alias I set up on my computer. You can see I'm using Mac, so it's just an easy way to open it up. So if I look, you can see this is the mesh. It's a bit coarser than the one you'll see online just because I coarsened it. And in this case, okay, the STL, because the resolution is a bit low, if I ran it finer, you can believe me, it's solids4foam. But I don't want to wait for the tutorial. But you can check on the website that the geometry has solids4foam. So in the tutorial online, it shows how to add a bounding box and refine it, and that Ivan created. And you can see it's like a mini tutorial for CFMesh, the open source version of CFMesh. So in this case, the STL was actually in inches. So if we convert it into meters, Yeah, it came from across the pond. So if I use a scale mesh, so scale mesh is built into CF mesh, but you can also use transform points is built into OpenFOAM, and that's scale. So if I just scale that mesh, reset it, and reset my view, you can see it just makes it smaller. The next thing I want to do is the patches by default will just be called wall, 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 wall. So I just want to change one of them to symmetry because it's a symmetry plane. So I will do that. So we go Emacs, constant polymesh, that's where the mesh is, boundary, symmetry. Just change this to symmetry. You can change these walls as well to be just patch. So I guess wall is just used for if you need a wall function, but the solver doesn't care about wall functions, so it doesn't matter. You can set it to patch, but it'll do the same thing if you leave them as wall. Okay, so we're almost ready to run the case. A couple of things just to point out. How is the case different from a classic OpenFOAM case? So it's not really, but let me just print out the tree, which let's see if we can actually see it. Okay, colors it selected are good. So if we look at the tree of the case, we have 0 directly like before. We have D because we're going to solve for displacement. So in literature, when I was learning solid mechanics, we call it U, but unfortunately, OpenFOAM calls U velocity, so we'll just call it D to avoid confusion. If we have some run scripts, this is just for power view. In the constant folder, dynamic mesh dict, gravity. There's a couple of extra things. So in solid mechanics, instead of transport properties, we're just using the mechanical properties, but that's just transport properties essentially. The two things which there's a direct analogy for multi-region foam is we just need to tell solids4foam solver what type of physics model to create. So we have a physics property file, and maybe we can get rid of this, but it's essentially just a file that says fluid solid or fluid solid interaction. So if you set it to solid, then it will expect a solid properties dictionary to say what type of solid. If you set it to fluid, it'll expect the fluid properties, what type of fluid, and if you set it to FSI, it'll expect FSI properties, what type of FSI. So then the solid properties is the only other thing. And then apart from that, the case is just like an OpenFOAM case. So if I open up constant solid properties, this is this runtime selection solid model. So I'm using something called linear geometry total displacement. So it's a linear geometry just means small strain. It's an assumption if the deformations are small and it's solving for total displacement. And there's some settings. I guess the analogy would be kind of like pimple settings, tolerances, and max iterations. And then if I open constant mechanical properties, which we saw there, this is the constitutive law. So, okay, the name here, steel, doesn't make a difference. If there's only one material, that name's not used for anything. But if I have multiple materials, that name, it will expect a cell zone with that name. So if I want to have multiple regions, then it will look for a cell zone with that name and it can complain if it doesn't exist. So linear elastic is just your basic one, but if you write banana, it'll tell you all the other ones that are available. Yeah, I'm mostly writing a material model. If it's well known and algorithms are out there, adding one is normally not that difficult, I would say. Touch wood. Very good. Some of the settings. So the last thing is I just want to update the boundary conditions. We copied this case, the 0D folder from another case with different boundaries and different boundary conditions. So we're just going to set the wrench fixed boundary to be fixed displacement 0, wrench loading to be an applied pressure of 0.5 megapascals. Wrench free is just the solid traction. It enforces 0 traction. So this we're using that for load and for free, but in one case it's 0, one case not. And then we have a symmetry plane. So I will be lazy and just copy all of these. So we go 0, B. So this was from the plate hole case. So I'll just paste this in and make sure I didn't mess up. Yeah, boundary field twice. So that is that. And okay, in this tutorial, it talks about relaxation factors and things like that. I don't think I'll need relaxation here. It doesn't hurt too much, but I'll probably just get rid of it. I don't think it'll do it. Okay, I think we're ready to run the case. So you can run it in parallel. Let me just check if it runs in serial, how long it takes. Okay, so we get an error. It says history patch not found. So there's function objects from the previous case that don't apply in this case. I'll just get rid of the function objects. So we can see there's some function objects down here, which I don't care about for now. Okay, so if I start it, it is not so fast, so maybe we'll just run it in parallel. So we go just running in parallel is like classic OpenFOAM. 4 domains, Scotch, fine, decompose bar. You can add a decompose bar dash cell dist as well. That will write to the 0 directory a folder, a field that you can view the decomposition in ParView if you want as well. Now I'll go MPI run for to like that. And I don't care about converting it to that either. So just to get some results to look at, I will reduce the max number of characters here. Actually, that's fine. We can wait. And get a drink. So while that's running, we get a couple of more seconds, we get there. So in this case, it's a small strain solver. So this is classic in finite element as well. So in that case, you actually assume the mesh doesn't move and is independent of the displacement field, which messes people's heads up sometimes, but you're solving for a field on top of a fixed mesh. So you get the displacement field, but the mesh doesn't change. So if you want to see the deformed mesh, you have to use this warp by vector field. So you can just warp the mesh by the field that you just solved for. Okay, so it reached the max iterations. It hasn't converged that tightly. You would normally converge it to 1 - 5 or 6, but it will have some results to look at anyway. So if I change it to decompose because it was in parallel, and then skip to the latest time step, and we should have a D field. Rescale it. So let's see, it's fixed over here. The force is over here. The displacement is going to be largest over there. That's not too exciting, but let's warp it. So warp by vector by the D field, or the point D field. If I warp it by 1, nothing really happens because it's steel, and we're just putting a small force on steel. So if you rescale that, auto rescale it, ParView will calculate some deformation just so you can magnify it. So you can see the mode of deformation. And this will be like if I use Abacus a lot, the commercial FEA software, and it just will check the bounding box and the magnitude of displacement and then scale it to be proportional to that. So you can see it. So you can see it bends around like this, and then you can look at, this is half the geometry. So if you want, you could reflect it to see the full geometry. And then you can look at the stress tensor. So the stress tensor, X, Y, Z, etc. So if that's X in that direction, so if you did solid mechanics courses, then you know that in bending, you get tension on top and compression on the bottom. So tension, compression. And then the equivalent stress, also known as the von Mises stress, is a scalar that might show for a metal where it will yield or permanently deform first. So we'd expect it here and here, or there's singularities at the end of the fixed point as well. And also you've got a strain tensor, so you can look at the strain components, and you can look at the hydrostatic stress as well, which is just the negative of the pressure. So you get something like that. So that's the general idea. So it's just like an OpenFOAM solver. Yeah, let me see if there's anything else. Yeah, okay. So let me keep going. So I've gone through all the details in these slides, but I'll skip over that. And then the slides I put online, I also given it another test case. But let me talk about FSI now. So that's just a solid mechanics test case, and I won't go through a fluid case test case. But the fluid test cases, OpenFOAM has fluid test cases, so solids4foam doesn't need those. But there's just 1 or 2 just to check that you get the same with pimple fluid as you do with pimple foam. But let's look at this flexible dam break test case now. So it's just dam break case, except we've added a little rubber dam. So these are your interfoam equations. In the solid mechanics, it's like before, but now we have a inertia term. And in fact, this is not actually correct. This is a small strain that the solver is actually set up to be a large strain formulation. And broadly speaking, in FSI, you have these interface conditions. So these kinematic conditions, which is say the velocity of the interface on the fluid side has to equal the velocity on the solid side. You have to have continuous velocity and continuous displacement, otherwise there'll be a gap. And that's called the kinematic conditions. And then the kinetic condition just says the forces should be equal and opposite attractions. So, okay, this n is a unique n, one of the n's, but if you have n fluid, then it will be equal to minus n solid. The coupling approach is like precise if you were precise, or this multi-region foam. It has a partitioned approach. You solve the fluid, then pass the forces to the solid, and then the solid you solve, it moves. Then you take the motion of the solid and pass it back to the fluid domain, update the fluid domain, and then you maybe iterate within a time step. So that's the main approach in solids4foam. So monolithic, I presented on Tuesday some initial development. So hopefully that'll be available maybe next year. But this is under development. So it's partitioned is the example I show now. And the same as multi-region foam, because it's actually using the same code for parallelization, which is okay way to do it, but there's probably a better way to do it is we reconstruct the entire interface across all processors and then sync it. And then each processor takes the bit at once. The problem is the fluid domain is decomposed independently of the solid. So processor one might get this part of the fluid and this part of the solid. So then if you need to transfer something across the interface, you need to find the right information. The easiest way to do it was this global patch, but there are other ways to do it. So the way the case is designed, the same as multi-region foam, it uses these region options in OpenFOAM. So in the zero directory, instead of just having velocity, pressure, displacement, we now have subdirectories called fluid and solid. So in the fluids zero directory is just zero fluid. The solid zero directory is zero solid, and the same applies to constant and system. So you'll have the fluid mesh is inside constant fluid polymesh. The solid mesh is inside constant solid polymesh. The same with system settings. And then there are some global settings. So we have, once again, this physics properties, this time set to FSI. And then we have these FSI properties, which gives the coupling approach. So I go to the test case. It is not this one, this one. Okay, so if I go constant physical properties, you can see it's at the fluid solid interaction. Well, you can sort of see. I can see. And then FSI properties, we have 3 coupling approaches. So in this, you basically say what's the solid patch or solid patches. This can be a list, and the fluid patch or fluid patches. So just for convenience, in this case, the patch is called interface in both of the meshes. And then you have some coupling methods or coupling tolerances and max iterations, etc. So then just to briefly look at the properties, I mean, the dam break case is essentially copied into the fluid folders. In this case, the dam shape, we changed it slightly because this FSI problem is a benchmark problem in the literature, and they use a slightly more slender dam so it deflects a bit more, and you get kind of more strange motion that makes it more interesting as a benchmark. But it's essentially just the dam break case. So you have U dynamic pressure, and actually you have a mesh motion solver now. So it's a moving mesh dam break case. So you need the ALE interphone essentially. So you have to have a mesh motion solver also. And in solid, we're just solving for displacement. Not going to go to full screen here because Zoom doesn't like it. And yeah, these settings. So to mesh the case or to set up the case, we're just going to use block mesh in this case. So block mesh, and many of the OpenFOAM utilities have a dash region option. So if we go block mesh dash region solid, it will put a mesh in the solid subregion, and the same with fluid. And then we need to set the initial alpha field, so set field dash region fluid. So I can do that now. So actually, if I just run the all run directory, it actually does all that, does block mesh, set fields, and then starts the solver. And while that's running, I can tail the output to see what's happening. So if I scroll up, it's basically goes to, let me see, iteration 1 to 0 here. So it will go to a time step, and then it will, initially in this case, it solves the solid equation as a predictor, and then it will go and solve the fluid equations. Then it'll transfer the force across the interface, interpolate it, and then solve the solid equations, calculates an FSI residual, and then does the same thing again, and it does a number of iterations either side. So you can see it's going through time here. So I will open this up. Perfect. Okay, set this way, and it's 2D case, so I'll set 2D. So here's our mesh. So PowerView is smart enough to recognize that it's a multi-region case. So it'll see you've got a fluid mesh. You can turn on and off, internal mesh, and also it will load the solid mesh. So it sees both of them. And if I go to the first time step, you can see some fields have partial because it's just for one of them. Displacement's only defined on the solid, whereas alpha is only defined in the fluid. But some of the fields like U, velocity is defined in both fields. So there's a velocity for solid and a velocity for fluid, and they should be continuous across the interface. So if I refresh it, I don't know how many time steps we have. Okay, we have some. So if I turn on the alpha water and we zoom a little bit down, so you can play it. Nope, go back to start. So just in the dam break case, it drops. And then when the water hits it, then you can see it bends it back and it moves. And you can see the mesh motion has to be solved as well. It's smoothing the mesh across. And the solid wiggles a little bit. And also in this case, just to demonstrate it, you can see the solid and the fluid are not conformal in this case. So we have a wrapper that essentially sits on top of AMI. So then we just explicitly use AMI to map, or GGI if you're in foam extend, or if they map directly, we just have a direct map, which is the same as what multi-region foam is using. So this just shows how it works. There's RBF implemented from an old port, but it's not so efficient for larger interfaces at the moment, the current implementation. So then you get something like this, and then you can look at your solid and you can look at the stresses in the solid as well. So it's bending again. It's a very coarse mesh, but you see bending on the outside and the other side. But when you don't have a conformal mesh, then you're always going to have little gaps like this as well. That's just the nature of the way you do it. So if that's too big, then it could cause a problem for the mapping. But in this case, we're calculating interpolation weights in the very first time step. So as long as they're okay, it should be okay afterwards because they're stuck. It's a no slip condition. So this very good. Let me see if there's anything else I wanted to show in this test case. Yeah, not really. I mean, this is a very whistle-stop tour. On the website, there's other benchmark cases. So there's one called 3D Tube, which is often looked at. It's like you apply, it's called a water hammer case as well. You apply a pressure pulse down a pipe with an elastic wall. It kind of mimics an artery or something like this. And then you get a pressure pulse travels down the pipe. So even though it's an incompressible fluid where the speed of sound is infinite, because of the compressible elastic wall, you get a pressure pulse traveling in the elastic wall, which causes a pressure pulse in the incompressible fluid, if that makes sense. So it's an interesting problem. People often use it to benchmark. You can look at the displacement of a point on the inside of the wall, and then you can look at how many iterations it takes, and you can look at the effective time step and coupling algorithms. And we were comparing to Precise and Atkins and different coupling methods, Tischler-Neumann and Robin coupling, and then the effect of these are the number of iterations, and then the effect of first and second order time schemes as well. So I'm not going to go through all of that now, but you can. There's lots of fun things you can play with. So the last thing I want to look at for the last 5 minutes, and then I'll leave maybe 10 minutes at the end if anyone wants to chat, is kind of just future directions. So I had a talk on Tuesday, and I talked about these Jacobian-free Newton-Krylov couple solvers. So these, as a step towards monolithic FSI implementations, then the problem is you make a very complex, big linear system, which is difficult to solve. And that means you now need to care about the linear solver and preconditioners for the linear solver. So Jacobian-free Newton-Krylov methods have some benefits, and finite element groups out there that have monolithic solvers seem to prefer these methods. So this is why I'm exploring them. So you could implement this yourself, and the group from Athens that presented yesterday, they have implemented their own Jacobian-free Newton-Krylov, but I didn't want to do that, so I'm using PETC. So I'm just loading a wrapper for PETC, and PETC is an open source toolbox for high performance linear solvers. So this code is all publicly available. If you want to try it out, there's the branch feature PETC SNES, and there's a preprint you can check out here, and it describes all the test cases. So initially I've looked at solid mechanics and some FSI coupling. So I tried bunches of different test cases. So I'll just show you how that's different and how to use it and what it looks like when you run this thing. So let me see. Oh yeah, before I show you that, just some of the speed ups. Okay, this is solid mechanics. I'm not saying this applies to the fluid solver, but this is a measure of speed up versus the segregated solution. So the Jacobian free solver was pretty much always faster. And if you look at most of the dots, this is logarithmic. So it might be 1.5, 2, maybe 3, 4 times faster, but in some cases it was over 100 times faster. So it certainly seems to be more robust, particularly for large deformations. It seems to be much more robust solver than our solid mechanics segregated solver. It remains to be seen for the fluid solver and FSI. But broadly speaking, there's only a couple of changes. So in solid properties, it's still the same solid models. I just add a new option called solution algorithm, which will default to the segregated. But if you want, you can switch it to PETC SNES. And SNES is the super, it's the not the Super Nintendo Entertainment System, it's the non-linear solver for PETC. And PETC, if you've ever seen PETC, they have an options file, and it's just runtime. You can define all the linear solver settings. That wasn't meant to do that. So if I look at a test case, I have one here. And let me just, I have a different version compiled. So I will just switch the library and we'll recompile it. I will switch it just to be the PETC version. So if I look at this test case, this is called an elliptic plate test case. So if I go back here, this is a NAFEMS benchmark, so National Association of Finite Element Methods. So it's like a curved plate, some symmetry planes, and they load it on top and it bends. And people can run analysis of this and they can see what it looks like and they can compare their solutions. There's no analytical solution, but there's numerical benchmarks, so you can check if your solver is as good or bad as other mechanics solvers. So if I want to run this test case with the Jacobian free, let me hide this thing, make this bigger. I'll delete the existing results. So constant solid properties. I just have this. I'm just setting it to PETC SNES. If I get rid of that, it'll just default to the original approach to segregated, like we saw for the wrench, or I can just specify that. But once I specify that, I can give an options file. So there's a variety of options you might use in PETC. So I've got one here called Hypera. So the PETC Hypera. I'm not going to go into all the details of this because it might be a bit overwhelming because PETC is a large software. But broadly speaking, at the top, the nonlinear solver is Newton line search. So it's a Newton method. And then you can tell it to use, it calls it matrix free, which it's not actually matrix free, but it's a Jacobian free method. And then I'm using this loose variant of GMRes. So loose variant of GMRes, it has a restart, but it also stores some of the directions from the previous restart as well. And then you can set things like tolerances. And then the important part then is the preconditioner. So I can set a LU, which would be a direct solver preconditioner. So then if it's a linear problem, the preconditioner just solves the problem and the iterative solver does nothing. Or you can use ILU. And the nice thing with PETC is you can do fill-in. So you can have as much fill-in as you want. And then in parallel, you can get Schwartz decomposition, whatever. So you can have fill-in across processor boundaries if you want as well. But I'm using Hyper here. So Hyper Boomerang is a PETC don't make it. They just have an interface to it. And it's a dedicated high performance multi-grid solver. So that scales very well. So if I think I've summarized the key points here, though, it's just the nonlinear solver, set a Jacobian free, linear solver, and then the preconditioner. So if I run this, what does it look like? So if I go solids4foam, it's a solving equation using PETC SNES. So this is they are the Newton iterations. So this problem is actually a linear problem. So since it's a linear problem, you could solve it in one Newton iteration. But I have a relative tolerance on the inner solver, the linear solver, just to drop it by 3 orders. So just because that's not a bad setting, just in general for nonlinear problems. So it's dropping the nonlinear, the outer residual from e to the 5 to e to the 1. And then it goes back in again and does it another couple of times. So it just does 2 iterations. And then this one is just the residual calculated. So these are absolute residuals. So it's dropping it by 9 orders of magnitude. But if it was a nonlinear solver, then you would see the quadratic convergence as well. You can do things like monitor. So SNES is the outer solver, but KSP is what they call a linear solver. So Krylov sparse. So if I turn on monitor, then when I'm solving it, you can actually see the linear solver being called as well. So you can see that's the linear solver and then the outer iterations as well. So I could set the linear solver to converge tighter, and in this case, it might be a little bit faster. And this runs in parallel as well. So in the code, it's using global indexing, and that will run nice in parallel, and then you can see these results. So even though I'm not going to show it here, there's also a solver called Newton IcoFoam, and then that is first steps at using the same PETC interface to do a block-coupled Newton IcoFoam, basically. Very good. I'm going to stop now. I know there's 10 minutes left, but I think it's late and people are tired. So yeah, if you have questions, feel free to ask, but yeah, hope you found this useful.